All right, so this video or this lab is all about distillation, right? So we're making some moonshine. We combined our sugar and with our yeast and some pasture salts, and we let that hang out kind of warm for like a week, and then in theory we should make some ethanol in there. And so now we want to distill that ethanol off and isolate it in its somewhat pure form, just to see what we can get. And the way we're going to do that is doing a macro scale fractional distillation. So I say macro scale specifically and underline that because you can do this on a smaller scale. So from last semester, remember we did the steam distillation and we used a Hickman head. That would be something that would be useful for a micro distillation. You would do more or less the same setup, except for on top of our column, which I'll describe in a second or in a little bit. We will put our Hickman head up here, okay? But we didn't do that this time. We did a large scale. And so that's why it is called the macro scale fractional distillation. So we've also done simple distillations as well, but we haven't done a fractional yet, okay? So simple distillation is pretty straightforward. It's the same setup, really. You have a boiling flask here. It goes up, and then it comes over, and then it comes out inside of a collection flask, right? That's pretty much it for it. But this one, inside, so I had two pictures here because I was like, dang, those look gorgeous. Like, I don't know which one to choose. So I chose both. Dang, those phones are crazy these days. You know what I mean? I did this with my phone. I have no idea how to take pictures without my phone to make it look good. But anyway, so inside here, we have our solution, right? Ooh, I probably don't want to have it dotted. Okay, so we've got our solution. It's got our water, sugar, ethanol, ideally, carbon dioxide, yeast, blah, 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 right? Or I filtered off the yeast. But the point is we got it heating up. And then inside of this, we were calling it a column because it is a reflux condenser. But we don't have, it's not empty. So what I've done, as you'll see in the video, is I've stuffed some like stainless steel sponge. You know those like wiry sponge looking things that you just scrape the crap out of things with? Well, that's inside of here. And so it's basically looking like this, right? Blah, 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 blah. Okay. So now as I heat this, it's going to go up and then it's going to condense. In here, which you can't really see that well, maybe you can see it on this one. But we have a little thermometer here. You can see the tip of it, and then up on the top, of course, with our little outlet adapter, right? It's attached here, boom, on the top of the distillation adapter. That's this guy. Boop, boop, boop. So that thermometer is useful because while you're doing a distillation, you want to get the temperature of the vapor, okay? And the vapor is going to essentially just kind of touch that. It's going to condense and then go down here as a liquid. And then it's going to drip down into this collection flask. So that's pretty much the process of distillation and fractional distillation. Now I'm going to go over the theory behind it. But first, really want to just tell you about the distillation. There's 4 methods of distillation, right? So we have the simple distillation and the vacuum distillation, fractional distillation, and steam distillation. So we've done steam, we've done simple, and then vacuum we won't do, but just know that if you wanted, you can apply a vacuum to this. So let's say here. And what that does is it decreases the pressure within the whole system. So if you have a boiling point liquid that has a boiling point of like 200 degrees, then we know as if you decrease the pressure within that system, then the boiling point of that liquid will also go down. And so it's actually a lot easier to distill that liquid now. Okay, so that would be like one of the benefits of a vacuum distillation. Super fun, but they're also kind of dangerous sometimes if you're not careful, because then if you do something silly, yeah, the vacuum within here, it could just kind of suck things out. or if you do a vacuum distillation and you shouldn't do a vacuum distillation because your liquid is not a high boiling point liquid. Definitely did that when I first started. But you learn from your mistakes, right? So pay attention in school, like right now. Let's see. So distillation theory. So distillation, by definition, is just the purification process by which a liquid sample is heated, thus vaporizing a liquid, and then condensing that vapor, and then collecting the condensate, which is that liquid, in another container. So that other container was here, right? Now that's just the definition of a distillation, right? So we have a couple processes here. So on the left, if we have a pure sample, pure A, for example, as we go on the y-axis on each of these, we have the temperature increasing as you go up. Okay, so let's go like that. I'll do this, increasing. And then the distillation progress as you go from left to right is basically it's time, right? Like we're heating it, and then it's going up, 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 up. Then temperature. And if we have a pure sample A, then the distillation process, so it's going to heat once it gets to temperature, like let's say here, whatever that is, let's say it was like 125 degrees Celsius. The distillation, like the vapors, as we would see on this thermometer right here, it's going to stay at 125 degrees the whole time. And that's just the inherent characteristic of a pure substance, right? They have a constant boiling point, and it's going to remain the same throughout the whole distillation process, 125 in this case, right? Now moving on to the second one here. If we have a mixture of compounds A and B and they have a close boiling point, okay, then the curve is more or less going to look like this. So it's going to heat up, heat up, heat up, heating up, heating up. Once it gets to here, it's going to start to kind of boil or whatever, and we're going to collect some liquids. The temperature will register at the boiling point here, but then it's going to start to go up, right? See how this peak goes up, 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 and then it's going to start to level out. And that's as we get to the two different substances. So this would be like B, and this would be A, right? And that's when they're really close, and it's really difficult to you can't, like, basically the composition of this distillate would be a mixture of A and B pretty much throughout. And that's because these boiling points are so close together, there's really no difference, and the distillation kind of just happens all at once. So we'll come back to this one right here. This is a mixture with higher boiling points, okay? So let's move on. So pure A, the temperature observed during the distillation of a pure substance remains constant, provided the liquid and the vapor are still present. So that's the key thing, right? The liquid and the vapor still need to be present. So that would be like liquid down here. Whoa, how'd I end up with a eraser? Liquid down here and then vapor up here. So once this liquid goes away, then it could just be heating up the air, and then if you turned it up to 11 and it's like super hot, then maybe the temperature will change, or it could just go down. It should just go down. But A and B mixture, the temperature does not remain constant, but increases throughout the distillation process, and then the composition of the vapor will vary continuously during the distillation. So pure A, the composition of the vapor is the same as the liquid, and it's always going to be the same because it's a pure substance. But for this one, A and B mixture with the close boiling point, it's going to vary throughout, okay? So I'll put close BP, okay? Now, a little bit more about phase diagrams. About distillation. We have a phase diagram here, and it's a vapor liquid diagram for a two-component system with A and B. Okay, so on the left, we have pure A, and then on the right, we have pure B, and these are their boiling points. Okay, so they're arbitrary. This is just a generic example. Okay, so On the left we have pure A, on the right we have pure B, right? So on a couple more things to point out. Look at the x-axis. We have in red on the left we have 100% A, but we also have a 0% B. And then in the middle, let's just say like right here, we would have 50% A and 50% B. But then maybe over here we have 20% A and 80% B. And then on the far right we have 100% B and then 0% A. Okay, and so what this represents on the left is the boiling point of pure A and then the boiling point of pure B on the right. I'm not sure if I said left and right, but I meant left over here, right over here. Okay, now the bottom line of this curve, so this one right here, that represents the liquid, the liquid composition, and then the top part represents the vapor composition. Okay, so for example, if I wanted to see when the vapor composition was 60%, we would go up, and it would be right at this point, which corresponds to that temperature, right? So that's basically what I'm referring to. And so, for example, the way it works, if you were going to do a simple distillation, you would basically, let's say we had 20% A. Okay, so we start here, and then we go up, boop, 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 and then it starts to boil. So that's basically the process of it heating. Temperature's going up, that's what the y-axis is, temperature, and then it's also increasing. As we go up, it's heating until it finally reaches this point right here. That's where the liquid starts to vaporize and it becomes a vapor. Okay, so now what's the composition of that vapor when we heat this 80-20 mixture? Well, what we do is we carry this guy over to the side, and then it hits this vapor curve, and then now what we can do is bring that back down. Okay, oh, I didn't make a straight line. Alrighty then. Okay, so now you can see that as we go down, we've essentially, if we're collecting this vapor, so that, remember, the vapor would come up into here, and then it would move its way down, and then we would collect it in a flask. That vapor would be collected, and we have an increased composition of A. So let's just let's see, if that was 50, this is like 58%. Okay, so that's 58%. Now, what that means, notice as we went from a 20% A, we went to 58% A, right? That's the new composition of that distillate. So if we collected a bunch of that, we could technically distill it again, right? So let's do that thing where we take that, put it in a new pot. So we would actually like take a bunch of it and then like throw it in a new boiling flask and then redistill it. And then we would go back up to this new liquid composition at 58%. So it's heating it, but then remember the vapor composition is different now, and that vapor composition is actually cruising on over here, and then that you bring it back down to the x-axis, and that's above, it's almost like 90%, right? So that's this graph that I drew, of course, so like that's not necessarily going to be the case, but it could be the case for some mixtures of liquids, right? So essentially what it took to get to 90-ish percent, almost like, let's say 88%, right? 88%, it took two simple distillations. Okay, now we could technically, let's do blue this time, do another one, could bring it back up, and then, I mean, it kind of looks like it's just right at 100%. So this, in this case, it would take like 3 distillations in order to obtain pure sample. But keep in mind, this first one over here that we collected, right, that 58%, that was 58% A, and what is that, 42% B, right? But that's just of that little bit that came over. Remember, there's still some in the flask, okay? So the reason why I'm mentioning this is because only a portion of A left, right? Or let's see, how do I want to phrase this? As A is leaving, right, we're increasing or we're decreasing the composition of A, right? And so let's say it went 20%, that 80-20 mixture, we heated that, and then we took out some sample of 58-42%, right? That means that more of A left than B. So whatever's left in that flask has a lower concentration of A, let's say 10%, right? And so what happens then is, as you distill, you have a lowering concentration of A, the lower boiling point liquid. And so that means that over time, as that lowers and lowers, it gets higher and higher in composition of B, and that means that the temperature of that solution is eventually going to go up, right? And so depending on the composition, starting composition, like you might have maybe A somewhere else and then maybe left some B behind. It really just depends. But the point I'm really trying to make is that as, let's say that first distillation, we lost mostly A and some of B, and we went down to 10%. Oops, sorry. That means that we would be at the 90-10 composition, and the boiling point, look at this graph, is higher, okay? But then it's whatever's left in there is a new composition starting point, and so that means we have this vapor composition, it's only 40%, and then we have to do another distillation, so on and so forth. And so long story short, simple distillations are okay, but they don't, every time you distill a sample and you obtain, let's say we started with that 80-20 mixture, we might, let's say we just, in like a great world, we got 50% of the solution separated from its original mixture, and then that was off of the first distillation. Oh, why do I keep doing that? And then we distilled that again, and we got another 50%, and then we distilled it again, and then we finally got another 50% of that, but at least it's pure. But notice that we're cutting it in half over and over again, and we're losing a lot of material. So having to distill over and over and over again kind of sucks, and it's not very efficient in terms of the purification of your sample. But let's say we had, and this would be the case if we had lower or closer boiling points for substance A and B. But let's say that we had a large boiling point, okay? Then it's a little bit different of a curve. So we would have right here this initial excuse me. I'm gonna leave that in there for you guys, but initially it comes at some temperature here, and then it's like a nice flat line. So what we could do is heat, collect, and then at this point switch the flask, as in this flask right here, throw that in the garbage, and then put a new one on there, collect while this is going up into a higher, much higher temperature, and then ditch that flask too, because like whatever is collected in this range is probably a mixture of A and B, and then once we get to the top, we're gonna have a cleaner composition of B. So this would be A down here, and on the right B. And so when there's a large difference in boiling point, it's very distinct temperatures, and so it's a lot easier to distill pure substances. So let's just say it was like 100 degree difference. That's pretty chill. You're going to be able to separate those using a simple distillation method, but that's not always going to be the case. So let's say ethanol and ethanol and water, for example. You have 78 degrees for ethanol, 100 degrees for water. That's 22 degrees, and that's actually pretty close. Or let's say you have toluene and benzene. So benzene is 85-ish, and toluene is 110. So like those are even too close. So in order to achieve separation of those, you want to use a different method, and that would be the fractional distillation. Okay, so let's see what I have on here. All right, so I do have another example of the simple distillation, and I like this drawing a lot better for you. So let's just say so this L1 right here is the liquid composition, right? And then the V1 is the vapor composition. L2 is the liquid composition, and then the V2, so on and so forth, right? So, oh no. Oh my God, I'm so sorry. Basically, you can look at these processes right here. So these lines going to, so L1 going to V1 and then L2. So L2 represents the one step, like one simple distillation, isolating some composition, roughly, let's say that's, what do you say that is? So let's just say that's like 25% A. So it went from like, what is that? Let's just say 5% A to 25% A. So that's like a solid improvement for sure. Fivefold. That was one distillation. Okay. And let's say we did another one. We took that same sample, L2, and then we heated it up to boiling. We got vapor 2, and then we collected the liquid 3. So L3, and that's definitely an improvement as well. So we went from 25%, from 5% to 25% to like 55%. Solid improvement again. And we could do it again and again and again, right? So these 5, so there's V1, L1 and V1 all the way to V5. So that's like 5 distillations, right? That could take a really long time. And like I told you before, you're going to lose a lot of stuff. And so it's not only tedious, but it's going to cost money and it's time consuming. And so that would actually be the benefit of a fractional distillation. So fractional distillation is actually almost like doing simple distillation, like let's say 5 simple distillations, but in one setup. So I told you before, this bad boy has some like stainless steel sponge in it, right? So it increases the surface area. This liquid vapor heats up, and then it you can't really see that in white right here. So liquid 2 and vapor 2 are in equilibrium, right? And so let's say they go up, they condense onto this this stainless steel sponge material, because it's a solid material, so they're going to touch it and they're going to condense into the vapor or liquid 2, right? And then they're going to go back and forth to vapor 2, and then they're going to go up and they're going to, oh my goodness, stop it. So then they're going to it's going to go up to V2 is going to go up to liquid 3, and then it's going to go back and forth to vapor 3 at this point, right? So I'm just basically trying to show you that within this column right here with the stainless steel sponge, the liquid or the ethanol solution in our case is going to go up. It's going to go in the vapor phase. It's going to condense. It's going to go into the vapor phase. It's going to condense over and over and over again. I've only drawn 5 examples here, but it could be a lot more. It could be like 1,000 times, or it could be 20 times, or whatever. It just depends on your setup. Okay. Now, so again, just L4 to V4, and then oh my goodness, I'm mad. and then L5 to V5, and then the last one, what I've drawn here, so as it's going back and forth, but then V5 at the top. So that's the vapor over here. And then that vapor comes along, and then it comes and condenses inside of this collection flask. And so in one setup, this demonstration, what this demonstrates is me doing 5 simple distillations, but only in one distillation. So that's the benefit and the idea of fractional distillation. Okay. And not only that, but I can actually still collect different fractions. So once I collect at some temperature that I've recorded here and it starts to go up, then I can take this flask out, exchange it with another one, which you'll see that I do in the lab. So that's the best way to go about it, is kind of switch out your flasks, and then you can test the composition of them and see if you want to combine them, or maybe you don't want to combine them, who knows. But one little vocab word that I want to give you is the forerun. That's basically the first fraction. So first fraction. And so in the case of ethanol, you want to typically discard the forerun fraction, usually in general, but especially in this case, because that forerun fraction is going to contain a lower boiling point compound called acid aldehyde, and you guys will need to figure out how that forms, but it's just a byproduct of the oxidation process in when you ferment sugar. Okay, so but again, forerun is the first fraction. Usually you just get a little bit, you toss that out, switch it out for the good flask, and then you collect, right? Just depends on what scale you're doing your stuff at. But the next thing I wanted to mention is the fact that these five distillations, right? This would be like considered theoretical plates. So if you're reading on, sorry, let me write that. So if you're reading about either like some different columns or distillation methods or whatever, you might see the word or the phrase theoretical plates, and it could be like 1,000 or whatever, but it could be 5 or 2. A simple distillation has 1 theoretical plate, and then sometimes you'll see columns. Maybe you've seen them before, but they have like these are called big row columns, where they have things like poking in diagonally. Those actually, the things beat up on it. These are about 2 theoretical plates. The stainless steel sponge inside of that column it's a little bit better than these 2 theoretical plates, the Vigro column, but it's not much better, and so you'll see the results are like whatevs. But the point is, theoretical plates are like the number of simple distillations that might be performed to achieve the same separation. But again, it's only in 1 fractional distillation, so it's super cool. All right, so the next thing. So the chart, the graph that I gave you before, you see that it's angled upward. Of course, you can swap that, right? So we could we can do the same thing. Sometimes you might see it like this, where we have only the percent composition of one thing as it increases, but this would represent one thing and this would represent another, but it's kind of like you get math, right? How to math. If this is 75% of something, then the other thing is 25%, right? So that's how that's gonna work. And it's the same idea as well, where you would if you have a 25% composition, you heat it up and it boils at this temperature, whatever that is, and then it goes to the vapor, and this vapor comes down and collects, and that is almost 50%. And then you take that again, and then it goes to here, and then, right? You guys get it. You guys are pros at this already. I can't believe it. You guys are so good. Like, how'd you guys get so good already? It's crazy. So then this would be like, boom, like it's taking forever to get this pure substance. Like I had to do it 1, 2, 3, 4, 5 again. Please, let me just do it one time. All right, do a solid fractional distillation, and then maybe you will. But maybe not. So here's the thing. There's this cool thing called an azeotrope. Oh, snap. Let me just give you the definition. So an azeotrope is a mixture with a fixed composition that cannot be changed by simple or fractional distillation. So that means you can't improve the composition by distilling it, even though that's kind of like how simple and fractional distillation work, right? So why is that? Because it behaves like a pure substance and it distills at the same temperature from the beginning to the end. So it's wild. The vapor and the liquid composition are going to be the same. And so what that means, if the vapor and the liquid composition are the same, they're not separated by this gap right here, right? That means that they must just be a point. And that's what this represents right here. So this point on this weird looking graph represents the azeotrope. Okay, and this represents the liquid vapor composition or phase diagram for ethanol and water. Okay, so let's say we had a 25% composition of, so this is blue is ethanol. That means we have a 75% composition of water, right? How to math? So bada bing, bada boom, you go up, you hit some boiling point, it's kind of high, like that's kind of messed up. And then it goes here. Boom. Let's just do it like this. I guess. So let's keep bringing it. Let's keep bringing it. And then we'll go here. So however you want to look at these distillations, basically, since this azeotrope has the lowest boiling point out of all of the combinations of water and ethanol, the azeotrope always comes off first. So let me draw. So azeo comes off first, and that's going to be at about like 78.1 degrees Celsius. Okay, well, the trippy thing is that this is about 78.3 degrees Celsius. So if your composition lies to the left, like, you're never going to achieve the 100% ethanol. You're just never going to get it because the boiling point of the azeotrope is below any other boiling point, right? And so your 78.1 degrees boiling point corresponds to about 95.6% ethanol, and so that's all you're ever going to get doing a fractional distillation. And you could do it a million times, it doesn't matter. You're only going to achieve 95.6% ethanol using this method, and that's again because it acts like a pure substance and it's going to boil at 78.1 degrees. And then if you set that aside and you collect it, remember that graph above right here, it's going to act like pure A, and this is going to be 78.1 degrees Celsius, and it's going to just chill there the whole time. And so that's why you're not going to be able to isolate it or purify it any further because it's fancy, it's an azeotrope. Okay, but I mean, if it is here, like let's say it's 98% already, then yeah, you can. But first, still, your azeotrope's going to come off until all the water is gone, and then you can isolate the rest of the pure substance, the pure ethanol. Okay, so that is an azeotrope, and that is pretty much what we're working with. That is why we cannot obtain pure ethanol. So how do you isolate pure ethanol? Well, you actually have to add benzene. Okay, so let me give you this. To isolate pure ethanol, aka ethanol aka what is it called again? Absolute ethanol. Absolute ethanol. Ethanol. You need to add benzene. Okay, so why do you add benzene? Because benzene creates another azeotrope. Okay, and it creates an azeotrope at a lower temperature. So I think it's like 68 degrees Celsius. And then it's benzene, H2O, and ethanol together. So once you still have to distill it off, and then once all of the water's gone, then you have your ethanol and benzene together, and those distill off as whatever temperature. It's like 70 something, and then you have technically no water, and so it's called absolute ethanol. And that's also why it's denatured. You can't drink lab grade ethanol, even though like it's 100%, right? You will die. It could be denatured with methanol, or it could be denatured with benzene. Either way, you're gonna die. Okay, so they get away with the reason why this is done. Like, you could technically purify it further from that point once you've gotten rid of the water, but when they sell it, they don't have to pay taxes on it's not like they have to have like a liquor license, because they're not selling the ethanol for consumption. They're selling it for chemical usage in in academia, right? So they don't have to pay the taxes, and it's like a ridiculous amount extra for a gallon. I don't know what it is. Nobody cares that much, but it's just more money for something that is unnecessary. So it's denatured to avoid it. And that's all she wrote. So real quick, simple fractional vacuum steam distillation, right? Soup's fun. Gorgeous pictures, right? iPhone, fancy. These are the different distillation methods, the different graphs for the distillation. We needed to do fractional distillation because our boiling points were really close together, and fractional distillation is pretty dope. You still need to do it low and slow. So anytime you're doing distillations, low and slow is still the best method. It's not really my style though, so you'll see in the video. It is what it is. What you need to do is calculate the percent yield just to kind of determine, or at least like the maximum that we could have achieved, just so you understand the level of like the volume of ethanol that we're really working with respect to the water. This will help give you a better understanding as to why this process might be kind of difficult. And yes, so this is some fun stuff. It's a really cool setup. We're legit making moonshine, and we fancy. Keep in mind everything I said. Okay, thanks. Bye. All right, so we've got 14 grams of sucrose, 1.4 grams of yeast, and then 14 mils-ish of pasture salt. So we're going to put them all in there. Shake that bad boy up, and then I'll be back. All right, so I basically poured all that stuff in there. Put a balloon over the top, so that way when carbon dioxide forms during this fermentation process, it has somewhere to go because that balloon will expand, but oxygen cannot go into this system. We don't want oxygen in there for further oxidation of our products. So that's why that's there. You can also set up a barium hydroxide bridge, but this isn't using barium hydroxide and it's less toxic. So I went that route. You do risk piercing the balloon popping off, so I taped it. You also risk having holes in the balloon, so you'll have to check on it frequently to make sure that it is in fact expanding or showing signs of evolution of CO2. As long as it's producing CO2, you are getting product. There's also this heat lamp here to allow for, I guess it's just warming this guy up, so that way fermentation works better, okay? Oh no. So the lamp is still on. But, oh, hello. Still hot, but this guy's not inflated much. It is a little bit. You can see, like, when I squeeze it, it still makes a bubble. So hopefully we just got, they just didn't really need to expand more than that. So it doesn't necessarily mean that we didn't form ethanol. Judging by the size of this, I don't really see. What you want to do is kind of inspect for some holes. I don't really see any obvious holes here, so that's good. It's, again, you can still squeeze it and form some like a little bubble there. So let's see what we can get out of this. You can see some kind of bubbles on the top, so that's cool. It looks like we're still evolving gas, maybe just not a crazy amount to force that to inflate to a significant amount. Let's check it out though. Let's what I want to do here is filter this and then take some and do a fractional distillation. All right, so what I want to do is pretty much take care of this guy. I want to transfer all of the liquid, not the solid material on the bottom. And I'm basically gonna go ahead and filter it and put it inside of a vacuum flask that is clean. You wanna make sure it's clean because we're using that material right there. We're gonna distill it, see how much ethanol we can get out of it. So really what I wanna do is, I wanna get as big of a filter as I can. So I got this giant Buchner funnel, but even though I washed it with soap, you can see that it's kinda gross. It's almost like we were doing Ochem with it or something. So what I want to do is place that on a vacuum filter and just go ahead. I did wash with soap. Soap doesn't always do the trick with Ochem, organic chemicals. And so I'm using a different flask because I'm just going to toss this in the proper waste container when I'm done. But I'm going to hit it with some acetone and see if we can get that cleaner. Okay, so hopefully we have enough acetone in here. But let's see. So vacuum on. You may or may not be able to see that, but squeeze that on there. Yeah, we definitely got some garbage here. Hit that. Ooh, so fresh and so clean. About to be. You could probably even see the yellow. Look at that. Oh my goodness. Nasty. Look at the yellow. So as good as you are at cleaning with soap, sometimes it just doesn't do the trick. Acetone does though. Okay, good. All right, so now what I want to do is, I don't want acetone to be in my ethanol either, so I'm gonna go ahead and turn this vacuum off. Throw the acetone away in the proper waste container and then rinse with a little bit of water and then be done with it. Then I'll go ahead and be back with you in a second with the filtration of the ethanol solution, okay? Okay, so let's do this, right? We want to filter this bad boy. So I'm gonna go ahead and turn that vacuum on. The first little bit, I carefully took this off so as not to disturb this solution right here. And so what I want to do is probably pipette a little off and then see how that goes for a little bit, okay? So let's get a little bit right on that filter paper, that way it doesn't seek underneath. Okay. And oh, that's gonna take forever, so I'm gonna go ahead and pour this up over like that. So I want to do this fairly fast because what I want to do is, after I filter it, I want to get the volume. So we see, you can see those bubbles forming. Why is that? Well, it's because there's gas in it, right? CO2. This is carbonated. This is carbonated drink. It's gross, yeasty, pasture salty
bubbly water, alcohol. It's a nasty mixed drink, something you don't want to drink. So, but basically, that's the bubbles. I just turned the vacuum off so that I wouldn't ruin this process and have all those bubbles get inside of the vacuum line, because that's never good. So check this out, check it out, check it out. We are almost done. So the idea would be slowly pour it for a couple reasons. So you want to slowly pour it because you don't want those bubbles to quickly go up inside of the vacuum line. But you also want to slowly pour it so you can have the clean solution that doesn't have any sediment go through first, so that way the filtration process goes a lot faster. Because as you can see, the bottom of that had a ton of yeastiness, and that yeast solid material is kind of clogging the filter, and it's taking a while. And so that's the purpose of kind of decanting the liquid slowly at first, so that you can minimize the clogging of that filter. So, because otherwise it would take forever, and you don't want to wait forever. Two reasons. I am going to measure the volume of this after I'm done, so that way I haven't decided yet. I might do small scale distillation, fractional distillation, just for the sake of time, or I might do a large scale. I already made a fraction column, but I'm looking for a piece of glassware to fit the top. So this is our little collection Hickman head. They don't go together, so super sad about that. I'm not sure I can actually make this guy work, so I might just have to do a big fractional distillation, but that's cool. So for now, you don't need to see that, right? That's boring. Y'all see my shirt though? What's up? Okay, bye. Be back. This is me making a bigger one. So I didn't get to explain the packing of this apparatus, the column. So for fractional distillation, as you know, from the lecture, you want some stuff inside of here to increase the, I guess, the number of like distillations, like theoretical plates. And so it's basically, as the liquid goes through here, it's going to go to the vapor phase. It's going to condense on this stainless steel sponge that I'm using, and then it's going to, after it condenses to a liquid, it's going to heat back up, go to a gas, and then do it over and 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 over until it gets to the top, at which point it can move on to the collection flask. And so right now what I'm doing is just packing it. Just wanted to show you that. I basically just shoved a long strand in there and pushed it down with a piece of something, right? Whatever you got to do. That wasn't bad. Okay, so it's off, and I'll go ahead and carefully take this off of here. Take this guy, just set him aside for now. And then what I want to do is measure the volume of this solution. It looks a little cloudy, like some sediment might have gotten through, but that's okay. Okay, so I went ahead and put all of that ethanol sugar pasture salt solution inside of that round bottom flask. We're gonna go ahead and use a sand bath. So what I did here is I left a little gap for me to basically be able to pour it in there, because I want to get it kind of low in there, and I don't know, I don't like wiggling it around so much. So I'll go ahead and just do this, and then we'll get it in there like that. That way the round bottom is kind of already inside of this this little sand bath portion, and then I can move on with my life once it's in there. Okay, so I'll do that. You don't need to watch me do that forever, but what you can see is that this guy is connected to a column with that stainless steel sponge in there. Then it's attached to the distillation head. So notice it just goes up and over. Okay, inside of there you can see
the tip of a thermometer. Okay, that thermometer is stuck through the outlet adapter, and you want to make sure that you're super careful with that. You don't want to like reach over and then hit that and break it, because then that sucks and you gotta clean up. And depends on if you have a mercury thermometer or an alcohol thermometer. Could be good, decent cleanup, or a terrible cleanup. But either way, be careful. You don't want to break stuff in lab, right? So this distillation head is attached to another water condenser that is not packed with anything, but will have water running through it. So remember, I have the water going in here, coming out, and gently, so as not to waste water, I have it like super slow flow. Got that slow flow. And then this is attached to this adapter here, and it's a vacuum. It's got a little vacuum thing here, but we don't need to pull a vacuum on this. We're just gonna run it at standard pressure, atmospheric pressure. And then once the this heats up, goes into the vapor phase, it's gonna hit some of this stainless steel sponge, and then it's going to condense to a liquid. Then it's going to heat back up, condense to a liquid, heat back up, condense to a liquid, over and 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 over again, until some of it gets pushed up into here, at which point I will see a boiling point temperature, or at least a fixed temperature. So I'll see this guy go up, 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 up until it gets in this region, right? And then it'll stay fixed. Once that stays fixed, then that's when I want to start paying attention and really just make sure that I'm noting that what temperature it's at when I collect my fractions. Okay, so that liquid will condense here and drip down, 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 down into here. Okay, so the first little fraction, what I want to do with that is throw that right in the garbage. Okay. So the first little fraction is going to be something else, and it's acetaldehyde. Okay, so acetaldehyde is a byproduct in this fermentation process, and sorry, I didn't know if I wanted to tell you or not, but I will tell you. You can just kind of deduce the mechanism for me later. But yeah, we don't want that. We always want to throw that first fraction out anyway, just a little bit collected in this flask, throw it right in the garbage. And then what we'll do is we can lower this bad boy right here, nice and easy. Notice I have all the clamps in the world on this, so that way I can just take this off and easily replace it with another round bottom flask, so that I can collect my desired ethanol compound. So once that starts to collect, I might do a couple fractions in there, but I want to really make sure that I'm paying attention to this temperature. If I see any changes, then I will immediately switch out my whatever I'm collecting in, my collection flask. Okay. Now, you also want to make sure that you note on that collection flask which fraction it is, the temperature, right? And then you might see it eventually start to shoot up, 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 and then maybe stop at 100. What's 100? Oh, that's weird. It's water. So once we start increasing the temperature of that distillate, and then we know we have to stop. Okay. So another thing I wanted to mention is that I could technically have this sitting in an ice bath to have it cool, and that will create a pressure differential that will make the process move pretty at a decent pace. But I'm not going to use ice. I'm just going to let the distillation go as it is, as it may, as it be. And so yeah, let's go ahead and get that started. All right, so I got that heat going. Turn that up to 11 or like 47. So I put some foil around there, so any heat that would have been lost out the sides or whatever is going to be bam right on that round bottom. Heat that bad boy up. Keep that column nice and hot too with the foil wrapped around it. You could use other things, depends on your setup, but foil is what we got, so that's what we're using. And then time for a snack, because it's about to be a minute. Okay, so it's been some time, whatever amount of time, doesn't really matter, but still not boiling. So like I can still touch it, which makes sense. I mean, only part of it's in that. I just couldn't get more of it inside of that sand. So we shall wait. Once it gets popping though, it goes fast. So we have to be careful, not get lazy. Make sure we're checking it regularly. Oh no! So you see some action, and we see some drippage. So what's the temp? What is it? Zoom in. Do better. There we go. What is it? This angle is poor. I'm sorry. I apologize. Yo, I'm just gonna tell you. It's actually like 84. So I'm gonna quickly change that flask out. Okay, bye. Okay. So now we are good. Let's see if we can. The temperature. Nope, you ain't getting that. But I changed it, so there's that. It's a bigger flask, but what is? So we'll go ahead and keep an eye on the temperature and make some changes when we need to. Okay, so what we got here is fraction 1, 2, and 3. I also just kind of switched it out and put a flask there. And the temperature, again, you can't really see it, is pretty high. It's at like 100 now, so that should just be water, right? So what we want to do is take these guys and measure the density, so that way we can identify the composition, percent composition of ethanol in this solution. Okay. Okay, so I put a beaker in there. I'm gonna go ahead and tear that. And now what I want to do is grab some water. Go ahead and open this bad boy up. I'm gonna measure what should be 1 milliliter of water, right? What's the mass of 1 milliliter of water? Oh, 1.02, good enough for me. All right, just wanted to make sure that this micropipette was actually a good one and measuring about 1 milliliter. I'm sorry, 1 gram per 1 milliliter of water. So now we can use it. Now we can use it to determine the density of our fractions to see, and then from there we can actually calculate using a chart the percent composition of ethanol. All right, so here's number 1, 2, 3. Get that one first. That's not even a mil. Let's go ahead. Angle that. So that way we actually get our sample in there. Go ahead, open this up. And transfer. Oh, check it out. 0.856. Write it down. Okay. That's the first fraction that we analyzed. All right, we got this guy. I cleaned them out, dried them up, teared them. Now we want to get the second one. Let's see what we've got here. Careful not to spill because I'm filming and chemistry-ing. I forgot my tripod again. So let's take a look-see. Ooh, 0.926, already garbage. All right, so 0.926, write it down. I want to take another one of these guys right here just because that second measurement wasn't so great.
have it. Okay, let's move on to the next one. I have a feeling that this next one's gonna be garbage. So what I'm gonna do is actually, well, I gotta transfer this back and clean it up. Let's take a look-see at the last one. All right, here we go. So we should expect it to get higher or lower. Okay, well, that is a thing. Let's take another sample of it. All right, so let's take another sample. Here we go, make sure none drips. Transfer this guy to our beaker. And see what we see. Oh yeah, ain't that a good one? We'll do another one just to average that bad boy out. You know what I'm gonna do though? I'm gonna go ahead and tear that. See if I've got enough in here. Let's go ahead and get rid of that. And then take some in. Slowly taking in the liquid. Oh, we don't have enough. I took in bubbles. All right, so let's see. Let's take some in, dump it. Transfer to our beaker, and what do you think it is? Ah! All right, well, okay. So what I want to do is just kind of get the volume of this. I want to see how much ethanol I got out of this bad boy. Spent hours in the lab. I'm trying to know how many shots we got. Just kidding, don't ever consume lab chemical. That's nasty. I wouldn't even think about that. That's nasty. Got methylene chloride in this lab. I don't even like, even though you guys are not here, I could like technically not follow the rules, right? No, I follow the rules because they're there for a reason. I do not eat in the lab, and I do not drink even water in the lab. My water bottle's in my office. I gotta keep leaving, going to get snacks, getting water, and that's why things happen when you walk away. Like this distillation popping off a lot faster than I thought. So you can see that's right below 2 mils, okay? That's probably, let me just tell you, 1.9, okay? So, let's get this next one. 1.9 for the first one. This went up to, a little bit in here. Not worth grabbing though. This went up to from 1.9 to 3.2. Okay, 3.2 for that one. You can see how like the liquid in here is definitely not water or not pure water. You can just kind of see the way it's rolling around and stuff. So 3.2 all the way up to 4. I mean, we could take a look at the rest of that distillate, but I mean, you saw the last density for that fraction 3. So you saw the density for fraction 3. And you saw that it wasn't very good. Oh, you know what? I forgot to get this stuff too. Pour that in there. Sorry, so the final volume that we actually collected and analyzed was 5 mils even. And you saw that the fraction 3's density was kind of all over the place because the quality of the equipment, but it was definitely below 75% ethanol, and which still isn't bad. I mean, if you don't know, 200 proof is 100% ethanol. So if you have 100 proof, then that means you have 50% ethanol, and then 80 proof, which is a typical vodka, is 40% alcohol, right? And I'm telling you, you're not in here, but like, ugh, smells like vodka for sure. And like yeah, no, that's nasty. My wife always makes fun of me because I just said that's nasty and I smelled it still. That's what I do. If you see it, it's like, is that chocolate or is that poop? I don't know. Give it a sniff. There's only one way to find out. 2 ways. You can taste it also. I don't roll like that though. I don't taste things that are presumably poop. Anyway, we got 5 mils. So that's 5 mils of like decent percentage ethanol. As you saw, the volume of the fraction, it got larger and larger, right? That was intentional on my part because I know that the good stuff is coming off first, and then I also paid attention to the temperature. So the temperature was starting to climb and climb and climb, and so I just swap it out, right? So if I really wanted to, what I could do is probably distill a little bit more, collect all of that. I did actually collect a decent amount. I'm just not going to analyze it, but then I could combine it with this and then distill it again. So that's actually the best way to kind of make sure that you get like very pure liquids, especially when you're working with azeotropes like ethanol and water. Forming that azeotrope, it's really difficult to kind of get a good amount of product in the end. But if you're really careful and you take your time on these distillations, they work really well, especially the fractional distillation. The reason, shoot, I lost my train of thought. I've been thinking. Okay, I want you to do the boiling point. Actually, I'm gonna do the boiling point. So let's burn some glassware. What you think? Okay, y'all are in for a treat. So taking this pipette, about to burn it, stretch it out, put it inside of this melting point capillary tube. Let's see if we can do this real fast. Nobody got time for messing around. Oh, let's make sure we get that hot, awesome, super duper awesome blue flame. Oh, too much oxygen. Or too much gas. There we go, look at that. Can't see it. Oh, there you go. See that blue flame? Woo! Check it out. So, man, I wish I wore the black shirt, huh? So y'all talking about practice, but so you can see the glass is what I mean. But here's what I want to do. Keep an eye on the glass, okay? So when I put it in here, gravity went ahead and bent that for me, right? So what I'm going to do is, when the glass softens, instead of letting gravity do the job, I'm going to stretch it this way. Let's see if we can make that work for us, okay? So remember, cold glass looks like hot glass, right? So this portion right here cools really fast, but this portion right here, when you heat the inside of the bigger part of the pipette, that stays hot. Okay, but I find that to be the easiest portion to manipulate for me, especially doing this part. Okay, so I went ahead and straightened that out. Go ahead and cool that bad boy off. This is actually a good way to make TLC spotters as well, because you can make them really fine, so that way you don't have a big blob on your TLC plate. And then if you have a big blob, you get a big blobs going up your TLC plate. It's not a good one. Okay, so I took my gloves off too because nitrile gloves are super flammable. Okay, so boom, 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 just rotating at the top of that cone. Can you see the top of that cone? Check it out, one-handed. What's up? What's up? What's that? And then occasionally what I'll do is I'll bend it like that just to see get an idea as to how soft it is, and then start pulling it apart. So this is hard to talk and do at the same time, but you see what I did here? I went ahead and stretched that out. Let me do one more time, but I'm not going to talk because I gotta focus. Alright, so I'm still talking. I couldn't help but talk. Let's see. So bending, keep going. Okay. So here's the thing. What I want to do now is kind of gotta wait for that to cool, but what I want to do is slice off a part of that small capillary tube. We call it a micro bell. Okay, so that micro bell is going to go inside of this here capillary tube. So this is the closed part. I want the open part of the micro bell to be on the top. Okay, let's see. But I also need to seal it. Okay, so let's see. Break that bad boy off. Okay, so now this side is open. Okay, that top part right there is open. So I'm going to carefully place this barely inside the flame down below. You see when you start seeing that yellow flame, or the yellow-orange, that means the glass is touching, and that means I don't want to put it any further than that, because if I put it any further, it's going to melt more of this little micro bell that I made, or at least the portion of the glass that I'm going to make the micro bell out of, and we don't want it to bend like we saw the, it did it. We don't want it to bend like that, because then it won't fit in the capillary tube. Okay? Less talky, more chemistry. Okay, so now I'm gonna go ahead and break this off. You could use like some glass cutters or whatever, but I do this instead because I'm careful and it's me. And if you were here, I would have you do something else probably. I would have you cut it off instead of using your hands, because then you get tiny shards of glass everywhere and also in your hand. I don't want you to do that. So now what I need to do is transfer a little bit of the ethanol solution to that boiling point tube. But here's the thing, it doesn't fit. They're like the same size. Okay, so what do we need to do? We need to stretch that bad boy out. Actually, I feel like I could just use this. I could use this one probably, the one I already made, this first one. Remember I was playing with it. That's what you want to do just to check is, see, my eyes are still good. You make sure that it fits inside. You also want to make sure that it fits kind of far down, because sometimes when you have viscous liquids and you want to put them in here to try this method, they get stuck up here, right? You want them to go all the way down to the bottom of the capillary tube, and then you want to place your micro bell in there, and if it doesn't go all the way down, then we're going to centrifuge it to push it down. Okay, and I'll show you the final product, because you might as well watch me. Don't believe me, just watch. Right? I'm not fudging this stuff. Okay. So now it's kind of hard to suck up with this tiny little pipette. Key to get it in there is don't breathe. I wasn't breathing the whole time, and I got it in there, and then I took it out on accident. But push it down, go ahead, fill it up, just a little bit. All you ever really need is a little bit. Flick it to make the liquid go all the way to the bottom, because it wasn't. You see? Do you see? Okay? Right there. Let's see. Well, you see. Now what we got to do is find our micro bell and carefully place that upside down inside of here. Dropped it. And I broke it. Gotta make another one, y'all. I'll be back. Actually, why don't you just watch me? Just watch me. Come on. Watch me while I work. Okay. So I used the other piece of that pipette that I already kind of thinned out. You may or may not be able to see it kind of stuck on the top. Should I tap it down and see what happens? Okay. So now what we want to do after this is take this to the melting point apparatus and then test, and then basically see what the boiling point is. And so the boiling point, I'll explain as we're doing. Okay. You may or may not have done this type of boiling point though on in like general chemistry or maybe intro chemistry or some other chemistry. But remember, the definition of a boiling point is the point at which the vapor pressure of the liquid is equal to the atmospheric pressure, and so it's going to start bubbling, and then it's going to go up. The gas inside of this capillary, this microbell, is going to come out, right? Because it expands. And then since it expanded, let's pretend my arms are the microbell. The gas, you're gonna, once it expands and the bubbles start to come out, then you're gonna turn off the heat to let it cool down. And then it's gonna start cooling down, and then that gas inside the microbell is going to condense, and it still has to occupy the entire volume of that microbell. And so as it condenses into a smaller gas or smaller volume, the rest of it is going to fill up with the ethanol solution. Okay, so microbell is this big, then the gas expands, right, to this big. So all this extra stuff pieced out as bubbles, and now we still have this microbell completely filled with hot air. As it cools to cold air, it occupies, let's say, half the volume, and then the rest of that volume needs to be occupied by liquid because that's all that's there. So it sucks it up, right? So, boom. And then the point at which the liquid goes up into the microbell is your boiling point. Bada bing, bada boom. Let's see how it actually works on our, so you can see this guy. You might be able to see the the capillary microbell, sorry, inside of this capillary tube. But I'll put it in there. Let's see if we can zoom in. So you can see the bottom of it. It's kind of floating up at the top, right? Had it. It's kind of where that bubble looking thing looks like it at the top. And then there is a broken piece of glass on the bottom, but like, who cares, right? Whatever, get off my back. So I tried. Fumbles. Okay, so I'm gonna go ahead and start it. I started it at 50. It says ready. I'm gonna click melt. So what we want to do is just pay attention, see what's going on, right? So we want to start noting when we see bubbles, and then basically record all of your observations, because you have no idea what you're looking at right now, for this is the first time you've ever done this, right? It's kind of like you get half credit too, because I'm doing it. But right now we are at 52. So what you want to do is look for some bublés, little micro bublés coming out of that capillary tube. And then once they start to bubble, we'll go ahead and just kind of keep an eye on that temperature. But we really want to just make sure that it's streaming like very fast, like super fast bubbles. Almost maybe even to the point where you can't see like individual bubbles, I guess. And then at that point we will stop the temperature. We will not turn it off. We'll just stop it, so that way it starts to cool. And then we can start keeping an eye out for it to see if it enters the capillary tube. I'm a little bit concerned that this is almost out of the window, because once the bubbles start to form, it might actually float up. So yeah, we'll see what happens. $58. It's gonna be a minute. I'll be back. No, there it goes. Oh, that's funny. So about that, pissed. See if I can't get that guy to go back down. I'm gonna pushing it with another pipette. Okay, so you can start to see some bubbles forming. It's a little weird in there. Not super ideal, but we can see some bubbles forming, right? Like bloop, 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 bloop. So let's keep an eye on it. It is at 86.4, so I mean, what ifs? It's not pure, or it's not 95% ethanol, but that's cool. I wasn't expecting that. I did combine all of the fractions, remember? So this isn't like the pure fraction or the best fraction that we had, the number one, where we had like maybe 75 or something percent. But this kind of demonstration is more so you can see how to do a boiling point. And you see the bubbles are starting to pick up. It's 89.7 now. Pick it up, pick it up. Still not super fast though, right? So let's see if we can, let's see. Still, whoa, bloop, bloop. I can't even see the glass in there, but I just know that bubbles are forming from it. Hopefully I'm not misled by something that I shoved in there. So let me take it out if I can. Yikes. Uh-oh. Alright, so I made two more, and it looks like the one on the left is actually looking pretty good. So let's try again. Oh, saw that bubble, right? Okay, so let's start. Melt it! We'll see what happens. I'll be back in a minute. Got bubbles. Slowly but surely at 75. Once things get popping, then we will figure out what we got to do, right? I already told you. To you, this probably seems like 5 minutes, but to me, this seems like, because it is, hours. It takes a long time to redo those things and make sure that silly old micro bell is chilling on the bottom. I'm about to be grabbing on a snack right after this. You know how I do, Red Bull as well. Got one in my fridge, in my office, so that way I don't have to wait. YouTube's been doing me dirty though. They're taking off my videos if I use music in them, so can't do that anymore. That's why I'm just gonna drop it like it's hot. Do my own thing. I don't need Justin Bieber to sing for me, or Beyonce, or Fleetwood Mac, Stevie Nicks. Get out of here. Yeah, you see those bubbles. 81. 81. 1. Whoa, look at it. Look at it. Look at it go. Oh, I'm acting a fool right now. I apologize, but also maybe you're welcome. I don't know. Maybe your day sucks. Maybe it's better now. Look at those bubbles. So right now it's at 84-ish, right? So I'm probably gonna drop this, turn this heat off. Stop. It says cooling. Burr, burr, burr. Cool it. Oh. Simmer down, Jess. Gotta get my life back together. Whoa. All right, cool. So you see how it's still bubbling, right? Well, now that it's cooling and the bubbles are coming out because the temperature or the vapor pressure. Sorry, I'm trying to think. Oh, it just went up. 82. You see that? It stopped bubbling because the liquid went up inside of the microbells because it's 82.
Okay, so I already gave you the explanation of this, but really now that you saw it actually go in to the capillary tube, or the microbell, that's technically the point where the vapor pressure is slightly below that of the atmospheric pressure, right? Because atmospheric pressure was pushing down and then it forced that liquid to go up. Right? And if the liquid inside of this capillary tube is pushing down at the same strength or pressure that the atmosphere is, shit, did I just say liquid? If the vapor from the ethanol inside of that microbell is pushing down at the same pressure as the atmospheric pressure, then nothing's gonna happen, right? But if once that gives, right, if the vapor pressure inside of the microbell is a little bit weaker, so less than that of atmospheric pressure, then the atmospheric pressure is going to win. It's going to push it down, and then the liquid is going to go up inside of the microbell. And so technically the temperature 82 is just below the boiling point of that liquid. Okay, because again, the boiling point of the liquid is when the vapor pressure of the liquid is equal to that of the atmospheric pressure. So it's about 82 though. Make sense? I'm sure we'll have questions. All right, as I disassemble this, I just wanted to show you, you can see there's liquid on there, right? And so that's something to think about when you're doing a fractional distillation on something, because if you don't have a lot, which we do, then you will lose some on here, right? Call them hold up.